Here's something that will mess with your head. Right now, we have telescopes powerful enough to photograph galaxies so far away that the light reaching us left before Earth even existed. We can see the large-scale structure of the cosmos, filaments of galaxy clusters stretching hundreds of millions of light years. We have captured images of stellar nurseries where stars are being born as we speak. And Pluto? The best image we had of Pluto before 2015 looked like someone photographed a blurry tennis ball through a foggy window. How does that make any sense? And that's just the beginning. Because once you start asking questions about Pluto, more questions pile up fast. Why do Pluto and its moon appear to orbit around literally nothing, an empty point in space? How did New Horizons photograph Pluto in such bright, crisp detail when Pluto is supposed to be in near total darkness, billions of miles from the sun? And the big one, the one that still makes people genuinely upset. Why did scientists strip Pluto of its planet status in the first place? These aren't just trivia questions. The answers reveal something profound about how light works, how gravity works, how science works, and how our understanding of the solar system has completely transformed in just a few decades. I'm going to answer all 4 of these questions today. Stay with me, because some of these answers are going to genuinely surprise you. Let's start with the telescope problem. If Hubble can photograph distant galaxies, why can't it clearly photograph Pluto? This one trips people up constantly, and honestly, the confusion makes total sense. Our instinct is to think, closer equals easier to see. If Hubble can resolve details in a galaxy millions of light years away, surely it can handle something right here in our own solar system. But that instinct is wrong, and understanding why it's wrong will change the way you think about observational astronomy forever. The key concept here is something called angular size, not how big something actually is in physical terms, but how much of your field of view it occupies, how wide it appears in the sky. And angular size depends on 2 things: the object's actual size and its distance from you. Let me walk you through this with a real example. The Andromeda Galaxy is approximately 2.537 million light-years from Earth. When most people hear that number, they picture something impossibly tiny and remote. But here's the thing. Andromeda is enormous. It spans roughly 220,000 light-years from edge to edge. That's so physically massive that even at 2.537 million light-years away, it still covers an angular width of about 3 full degrees across our night sky. For reference, the full moon covers about half a degree. Andromeda is 6 times wider than the moon in the sky. It's so large, in fact, that Hubble cannot photograph the entire thing in a single image. The famous deep-field images of Andromeda you've seen are actually composites, mosaics stitched together from hundreds of separate Hubble exposures. The telescope had to be pointed in multiple directions just to capture chunks of it. Other galaxies are similar. The Pinwheel Galaxy sits about 21 million light-years away, nearly 10 times farther than Andromeda. And yet it still spans nearly the same angular width as the full moon. From Earth's perspective, that galaxy covers a meaningful patch of sky. That gives Hubble something to work with. Detail becomes possible. Now let's look at Pluto. To measure angular sizes precisely, astronomers use a system of degrees, arc minutes, and arc seconds. 1 degree contains 60 arc minutes. 1 arc minute contains 60 arc seconds. So when we say Andromeda is 3 degrees wide, that's 10,800 arc seconds across. Pluto, at its closest approach to Earth, has an angular diameter of approximately 0.11 arc seconds. Not arc minutes, arc seconds, and not even a whole arc second, a tiny fraction of 1. To put that in perspective, that's roughly 100,000 times smaller than Andromeda's angular width. Pluto is so physically small, just 1,477 miles in diameter, and so far away, nearly 3 billion miles at closest approach, that it essentially vanishes into a point of light even in Hubble's most powerful instruments. The fact that Hubble can resolve any surface detail on Pluto at all is actually a minor miracle of engineering, but the detail it can extract is extremely limited. The famous blurry Pluto images from Hubble before New Horizons, those were genuinely the best we could do. Not because our telescopes weren't powerful enough, but because physics set a hard limit on what was possible from Earth. This is exactly why the New Horizons mission was such a massive deal when it launched in 2006. The only way to truly see Pluto was to go there. You can't observe your way out of an angular size problem. You have to physically close the distance. And when New Horizons finally flew past Pluto in July 2015, after 9 years of travel, covering more than 3 billion miles, the images it sent back were stunning. Mountain ranges of water ice, vast nitrogen glaciers, a heart-shaped plain now named Tombaugh Regio, atmospheric haze layers, things nobody had predicted, things nobody could have seen from Earth no matter how good the telescope. So next time you see a breathtaking Hubble image of some distant galaxy, remember, those galaxies are enormous. Pluto is tiny. Size and distance together determine what we can see, not just distance alone. All right, here's one that sounds like it belongs in a science fiction plot. If you look at time-lapse footage of Pluto and its largest moon, Charon, moving through space, something immediately seems off. They aren't orbiting each other in the way you'd expect. The way Earth orbits the Sun or the Moon orbits Earth, with one object clearly in the center and the other circling around it. Instead, both Pluto and Charon appear to be circling a fixed point that sits between them, a point in what looks like completely empty space. No object there, nothing visible, just a gravitational anchor hanging in the void. The first instinct for a lot of people is a wild one. Could there be something there? Something invisible? A concentration of dark matter? A small, lurking black hole? Here's the thing. Scientists actually expected this behavior before New Horizons confirmed it up close. And the explanation requires zero exotic physics. Everything in the universe that orbits something else doesn't orbit the center of that object. It orbits the center of mass between the two objects. In physics, we call this the barycenter. Picture a rigid bar connecting two objects, one massive, one small. If you wanted to balance that bar on a single point, you wouldn't put the fulcrum in the geometric middle. You'd slide it toward the heavier side. The barycenter is that balance point, the true center of mass for the entire two-body system. Now, in most planet-moon systems, the planet is so enormously more massive than its moon that the barycenter sits deep inside the planet itself. Earth is about 81 times more massive than the moon, so the Earth-Moon barycenter is located roughly 1,000 miles beneath Earth's surface. The moon orbits that point. Earth wobbles around it slightly, and to the casual observer it looks like the moon just orbits Earth. Pluto and Charon are completely different. Charon is about half the diameter of Pluto and has a mass roughly 12% of Pluto's. In planetary terms, that's extraordinarily close in mass for a planet-moon pair. The result is that their shared barycenter, their mutual center of mass, sits outside of Pluto entirely, hanging in open space between the two bodies. Both Pluto and Charon orbit that external point. Neither one is truly orbiting the other. They're locked in a gravitational waltz around a shared center that neither of them physically contains. This is so unusual that many astronomers refer to Pluto and Charon as a binary dwarf planet system rather than a planet and its moon. There is one other well-known example of an external barycenter in our solar system, the Sun and Jupiter. Jupiter is so massive, more than twice the mass of all other planets combined, that the Sun-Jupiter barycenter actually lies just outside the Sun's surface. The Sun itself wobbles around this point as Jupiter orbits. That wobble, by the way, is exactly how astronomers detect exoplanets around distant stars. They watch for stars that appear to slightly oscillate, betraying the gravitational pull of an unseen planet. But back to Pluto. The empty space orbit isn't a mystery. It's just physics doing exactly what physics does. The math works out perfectly. There's nothing hidden there. Just two small worlds, gravitationally committed to each other, spinning around their shared center of gravity as they travel the outer edge of the solar system together. This is one of my favorite misconceptions to unpack, because the surprise people feel when they look at New Horizons imagery is completely understandable. And correcting it teaches you something genuinely useful about light, cameras, and the nature of darkness. The assumption goes like this: Pluto is nearly 40 times farther from the Sun than Earth is. At that distance, sunlight must be essentially non-existent. So how is Pluto lit up so clearly in photographs? Shouldn't it look like a dark rock floating in blackness? Let's start with the actual numbers. The intensity of light follows what's called the inverse square law. Double the distance, and the light intensity drops to 1/4. Quadruple the distance, 1/16 the intensity. At 40 times Earth's distance from the Sun, Pluto receives roughly 1/1600th of the sunlight that Earth gets. Earth receives approximately 100,000 lux of sunlight on a clear day. Divide that by 1,600 and you get somewhere around 60 to 65 lux at Pluto's surface. 60 lux. What does that feel like? Think of a well-lit office hallway, or a shopping center parking garage with decent lighting. Or that moment just after sunset when you can still clearly see everything around you, but the sky has gone deep blue. It's dim, no question, but it is absolutely not total darkness. It's not even close to pitch black. NASA actually created a tool around this concept called Pluto time. Twice a day, at dawn and at dusk, the light level on Earth's surface momentarily matches the light level at Pluto's noon. You can look up Pluto time for your specific location, and when that moment arrives, go outside. Look around. Notice that you can see perfectly well. Notice that a modern smartphone camera handles it effortlessly. That's Pluto at high noon. Now factor in camera technology. New Horizons carried a scientific imaging instrument called LORRI, the Long-Range Reconnaissance Imager. It was engineered specifically for low-light deep space photography. One of its key capabilities is adjustable exposure time, the ability to keep the camera sensor collecting light for extended periods. The longer a camera's shutter stays open, the more light accumulates, and the brighter the resulting image. We use this same principle on Earth all the time. Night sky photographers set exposures for 15, 30, or even 60 seconds to capture stars and the Milky Way that are completely invisible to the naked eye. Your phone does a version of this in its night mode. The principle is ancient and simple. If you can't see something because it's dim, wait longer and collect more photons. Then there's post-processing. After receiving the raw image data, transmitted across billions of miles of space, arriving as a faint signal that took hours to reach Earth, scientists adjusted brightness, contrast, and color balance. This isn't fabrication or artistic enhancement for the sake of aesthetics. It's standard calibration. Every space image you've ever seen has been processed. Raw sensor data almost never looks like the final released image. There's also one more factor that people rarely consider: Pluto's surface reflectivity. Pluto is covered largely in nitrogen ice, methane ice, and carbon monoxide ice. These materials are highly reflective. They have a high albedo. Pluto's average albedo is around 0.52, meaning it reflects roughly 52% of the sunlight that hits it. Some regions, particularly Tombaugh Regio, are even more reflective, nearly as bright as fresh snow. Compare that to our moon, which has an albedo of about 0.12. Pluto reflects more than 4 times as much light per unit area as the moon does. Put it all together: 60 lux of available light, a precision low-light camera with extended exposure capability, professional post-processing, and a highly reflective icy surface, and suddenly those crisp, illuminated New Horizons images aren't mysterious at all. They're exactly what good science and good engineering produces. Pluto is dim. Pluto is not dark. There's a meaningful difference. Okay, this is the one. This is the question that generates more emotional responses than almost any other topic in popular astronomy. People feel genuinely wronged on Pluto's behalf. They grew up with 9 planets. They had the mnemonic memorized. And then in 2006, the International Astronomical Union held a vote. And suddenly the solar system had 8 planets, and Pluto was something called a dwarf planet, which sounds, frankly, like an insult. The outrage is understandable, but the full story is far more interesting than the headlines suggested, and it starts not in 2006, but thousands of years ago. Here's something most people don't know. The number of planets in our solar system has changed many times throughout history, not because planets appeared and disappeared, but because our understanding of what a planet is kept evolving. In the ancient world, there were 5 known planets: Mercury, Venus, Mars, Jupiter, and Saturn, because those were the 5 points of light that moved noticeably against the fixed background of stars. Some Greek astronomers also included the sun and moon in their planetary count, though that convention never became universal. For roughly 2,000 years, 5 planets. That was the solar system. Then, in 1781, William Herschel discovered Uranus through a telescope. This was genuinely revolutionary. For the first time in recorded history, a new planet had been found. The concept that there might be more worlds beyond what the naked eye could see suddenly became real. Astronomers began searching in earnest, and they found things. Starting in the early 1800s, a series of objects were discovered in the region between Mars and Jupiter. Ceres in 1801, followed by Pallas, Juno, and Vesta over the next few years. And here's the part that tends to shock people. These objects were all initially classified as planets. Textbooks of the era listed them alongside Mercury, Venus, Earth, and the others. At one point in the early to mid-1800s, the solar system was considered to have over 20 planets. Then more objects kept appearing in that same region, and more, and more. By the 1850s, the pattern was undeniable. There wasn't a scattering of individual planets between Mars and Jupiter. There was an entire belt of smaller bodies, fundamentally different in character from the major planets. The term asteroid was adopted, the belt was recognized as its own class of object, and Ceres, Pallas, Juno, and Vesta were quietly reclassified. The planet count dropped back down to 8, with Neptune, discovered in 1846, now included. Hold on to that history because it's going to be important in a moment. In 1930, a young astronomer at Lowell Observatory named Clyde Tombaugh discovered Pluto. It was immediately and enthusiastically declared the 9th planet. The discovery made international headlines. School children were excited. The name, suggested by an 11-year-old in England, stuck. Pluto was in the family. But complications emerged almost immediately. First, Pluto's orbit was strange. Unlike the 8 major planets whose orbits lie roughly in the same flat plane, like rings on a tabletop, Pluto's orbit is tilted about 17 degrees off that plane. It's also highly elliptical, meaning it's not a near circle like Earth's orbit, but more of an elongated oval. This elliptical path is so pronounced that at certain points in Pluto's 248-year orbit, it actually comes closer to the Sun than Neptune does. From 1979 to 1999, Neptune was technically the outermost planet. Unusual, but not disqualifying on its own. Then came the size problem. Early estimates of Pluto's mass were wildly off. It was initially thought to be roughly Earth-sized. Over subsequent decades, better measurements kept shrinking that estimate. By the 1970s, it was clear that Pluto was far smaller than anyone had thought. When Charon was discovered in 1978 and allowed precise mass calculations, the true figure became apparent. Pluto has a mass of only about 0.2% of Earth's mass. Our own moon is more than 5 times more massive than Pluto. This raised uncomfortable questions. If Pluto is smaller than Earth's moon, why is it a planet while the moon isn't? No satisfying answer existed. But Pluto still held its designation. It was grandfathered in, so to speak. The real crisis came in the 1990s and accelerated into the 2000s. Telescope technology had improved dramatically, and astronomers began finding objects in the region beyond Neptune, objects that looked remarkably similar to Pluto in size, composition, and orbital characteristics. This region came to be called the Kuiper Belt, and it was clearly Pluto's neighborhood, a vast ring of icy bodies stretching from about 30 to 50 astronomical units from the Sun. Pluto wasn't a lone outlier, it was a member of a population. Then, in 2005, astronomer Mike Brown and his team discovered Eris, a Kuiper Belt object that appeared, based on initial measurements, to actually be larger than Pluto. If Pluto was a planet, Eris was a planet. And there were other candidates emerging as well: Makemake, Haumea, Sedna. The International Astronomical Union faced an impossible situation. Either accept dozens of new planets as more Kuiper Belt objects were found, potentially ending up with 50, 100 or more official planets, or establish a clear, scientifically coherent definition that drew a meaningful boundary. In August 2006, they voted on exactly that. The IAU defined a planet as a celestial body that orbits the Sun, has sufficient mass for its gravity to pull it into a roughly spherical shape, and has gravitationally cleared the neighborhood around its orbit of other debris. Pluto satisfies the first 2 criteria without question. It orbits the Sun. It's spherical. But criterion 3? Pluto sits embedded within the Kuiper Belt, surrounded by thousands of similar objects. It has not cleared its orbital neighborhood. It never could. It simply doesn't have enough mass. Under the new definition, Pluto was reclassified as a dwarf planet, a body that meets the first 2 criteria but not the third. Now, this decision was and remains genuinely controversial within the scientific community. Some astronomers argue that clearing the neighborhood is a poorly defined criterion that, strictly applied, would disqualify even Earth if relocated to the outer solar system. The debate is real, ongoing, and legitimate. Science doesn't always settle things cleanly. But here's the perspective worth holding on to. The IAU didn't demote Pluto because they decided it wasn't special. They reclassified it because our understanding of the solar system had fundamentally changed. We now knew that beyond Neptune was an empty space punctuated by a single oddball world. It was a vast, dynamic region populated by an entire class of objects that we were only beginning to understand. Pluto was reclassified the same way Ceres was reclassified in the 1800s, not out of spite, but because a more complete picture of reality demanded a more precise vocabulary. And Pluto itself? Still there, still extraordinary, still covered in nitrogen ice mountains and carbon monoxide glaciers and a mysterious heart-shaped plain that we still don't fully understand. Still holding 5 known moons, still drifting through the outer solar system on its long, tilted elliptical path, entirely indifferent to how humans categorize it. The label changed. The world did not. So there you have it. 4 of the biggest questions people ask about Pluto, and 4 answers that, I hope, gave you not just information, but a genuine window into how science actually works. We learned that what a telescope can see depends not on distance alone, but on angular size, the interplay of physical scale and distance that makes a galaxy easier to resolve than a tiny ice world in our own backyard. We learned that orbital mechanics doesn't always look the way we expect, and that Pluto and Charon's shared gravitational waltz around empty space is one of the most elegant examples of the barycenter principle anywhere in the solar system. We learned that dark and pitch black are not the same thing, that Pluto's surface receives enough sunlight to be imaged clearly by a well-engineered camera, and that NASA's Pluto time lets any of us experience that light level for ourselves twice a day. And we learned that Pluto's reclassification wasn't an act of scientific cruelty. It was the natural result of discovery, the same process that transformed our understanding of the asteroid belt. And that will almost certainly continue to transform our understanding of the outer solar system as new objects are found. The universe doesn't care about our categories, it just keeps surprising us. If this video sparked new questions for you about Pluto, about the Kuiper Belt, about the nature of planetary science, drop them in the comments. Every question is worth asking. Every answer leads somewhere unexpected. That's the whole point. Thanks for watching. See you in the next one.